The definition of momentum is the quantity of motion of a moving object. In order for an object to have momentum, it needs both velocity and mass. So if an object is not moving, if it is stationary, that object will not have any momentum because that object has no velocity. So it needs velocity, it needs to be in motion in order to have momentum. The higher the momentum of the object, the harder it is going to be for that object to stop. To calculate momentum, we're going to be using the following equation, P equal to mv. So P is the variable representing momentum, m is representing mass, and v is representing the velocity, since momentum, we just said, is dependent upon the object's mass and the object's velocity. The larger the mass of an object, the higher its potential momentum. Also, the faster the object's going, so the higher its velocity, the higher its potential momentum. When we calculate momentum, the units are going to be kilograms times meters per second. So that's what we're seeing down here. So the kilogram is representing the mass. So whenever we calculate momentum, we need the mass in kilograms. And then this meters per second portion is due to the velocity, because velocity needs to be in meters per second when we calculate problems in physics. Once again, if the object is at rest, the momentum is going to be zero because it will have zero velocity. And to calculate momentum, we take mass times velocity. So object not in motion has zero momentum. Let's look at a comparison of momentums. So we have here a soccer ball and a truck. Now a soccer ball, its mass is less, its velocity is also less than that compared to a truck. So in order to stop a soccer ball, it's going to be easier to stop a soccer ball than it would to stop a truck for these reasons, because of their mass, because of their velocities. So if we wanted to stop a soccer ball, all we need is a net, because it's easier to stop due to its smaller momentum. If we wanted to stop a truck, however, we need larger force to stop it. So in this example, we have a wall stopping the truck. Another comparison, so now we're looking at a supertanker and a bullet. Now, just at first glance, if you looked at just the masses of both of these objects, you would assume that the bullet would have a lower momentum. But it doesn't. Their momentums are actually comparable. So a supertanker, yes, has a very large mass. It's huge, right? So large mass. But its velocity is going to be very low because supertankers don't move very fast. So due to the fact that it has a low velocity, the momentum of a supertanker is very similar to the momentum of a bullet. A bullet, yes, is small. A bullet has a small mass, but its velocity is so high, it's going at such a high speed that its momentum is still very great. So the point I'm trying to make is make sure you're taking into account not only the mass of the object, but the velocities as well when calculating momentum. So let's look at this example. So we have a 1,800 kilogram car going 30 meters per second, and it's hitting a 4,500 kilogram truck that is going 10 meters per second. So we have a collision. So which vehicle do you expect, the car or the truck, to have greater momentum? Now at first glance, you're probably going to assume that the truck has a greater momentum because it's bigger, right? More mass. But make sure you're taking into account the velocity as well, because if you'll notice, the car is going faster. It has a higher velocity. It's going 30 meters per second, where the truck is only going 10. So let's do the calculation and see if it is the truck or the car that has the higher momentum. So to calculate, we need to take mass times velocity. So for the car, its p-value, its momentum, we're going to take its mass, which is 1,800 kilograms, and we're going to multiply it by its velocity, which is 30 meters per second. So multiplying those two, we get 54,000 kilograms times meter per second. Now let's look at the truck. Same calculation, but different values. The truck has a higher mass, 4,500 kilograms, but it is going slower, so 10 meters per second. Calculating that out, we get 45,000. So, which one, the car or the truck, has a higher momentum? The car, because of its velocity. Now let's look at momentum and force. So we're going to bring back force, which we were talking about in chapter 5. So to stop an object with a large momentum, you're going to need either a large force, which means stopping the object quickly, or a small force applied for a long time. Okay, so think back to the example that I showed earlier of the truck running into a wall. Okay, so a truck has a large momentum if it is going a certain velocity, a certain speed, right? It has a large mass, and then it has the potential to have a large velocity, so it's going to have a large momentum. So to stop that truck, we're either going to need a large force, such as the wall, the truck running into a wall, because that will stop the truck. It's a large force acting upon that truck. But if we run into a wall, right, we're going to be stopping that object quickly. That truck's going to stop very fast. And there's going to be injuries. The other option to stop that truck with that large momentum would be applying a small force over a long period of time. So that would be, instead of running into the wall, if you applied the brakes. Because if you press on the brakes, you're just applying a small force, but you're applying it over a longer period of time. It's going to take longer for the truck to stop using the brakes than if you ran into a wall. Okay, so changing an object's momentum is going to depend upon the force applied, but also the time interval in which that force was applied. So are you stopping it quickly or are you stopping it slowly? So here we're going to have our first equation for impulse. So what impulse is the change in momentum. Okay, so impulse is the change in momentum. So when you are stopping an object, you are changing its momentum. Its momentum is going from, say, 4,500 kilograms times meters per second down to 0, right? The impulse is the change in momentum, and we just said that change in momentum, or to stop an object, is dependent upon force and time. How much force are you applying, and how long is it taking to stop that object? So this is our first equation that we're going to have for impulse, where we're taking the force applied times the time interval, the time it took to stop. Looking at this equation, force and time are inversely proportional. So when we talked about inverse proportionality, we said it meant that if one goes up, the other goes down. Okay, so what that means is if you're applying a large force, so force is going up, the time is going to go the opposite direction, down. So think of that truck running into that wall. Large force, so force is high, time low, opposite directions. Okay, but now think of applying the brakes to the truck. That's a low force, so force is going down. Since it's inversely proportional with time, that means time is going to go the opposite direction, up. So if the force is low, down, the time is going to be longer, higher, going up. Therefore, increasing the time can actually decrease the force felt. So this is a concept that has been applied to many safety measures. So let's look at some real-world applications using this inverse proportionality. So we just said if you can increase your contact time, make the time go up, you can decrease the force. And this has been very helpful in the real world. So this is the reason that we have padded dashboards, for instance, in cars. Because by applying that padding, what you're doing is when someone gets in an accident and they hit their head on the dashboard, it's increasing the contact time of their head on that dashboard because their head has to go through all those layers of padding before it hits the harder surface. So their contact time with the dashboard goes up, and this means that the force they feel now is going to go down, opposite direction. It's going to lessen their injuries. It's the same reason why in gymnastics and wrestling you have padded floors. Because when that gymnast, that wrestler, even in boxing matches, right? When they hit that padding, their contact time is increased because they have to go through all those layers of padding before they hit the hard floor. So since the contact time went up, the force felt goes down, less injuries, right? Same in boxing, they wear padded gloves because that's going to increase the contact time, lessen the force, lessen the injuries. So let's look at impulse and momentum. So we just looked at impulse and force. Now let's look at impulse and momentum. So impulse, we said its definition was the change in momentum. Okay, so if you ever have change in anything, it's usually represented by this triangle, which is called a delta sign. So delta P is the change in momentum. Whenever you have change in something, it's always final minus initial. So impulse is going to be final momentum minus the initial momentum. So substituting our equation that we have for momentum, which is P is equal to mv, into the above equation, we get a new equation for impulse, which is mass times final velocity minus mass times initial velocity. So when we use this equation, we are calculating the change in momentum of a specific object. So the mass is going to be the same in both spots. So this m here is going to be the same value as this m because we're talking about one object. It's the velocities that are going to be different. So the final velocity is going to be different than the initial velocity. And I'll have a video showing me working through some of these calculations and how to use them. So when using this equation, m is the mass of the object, just like when we were using it in momentum, and mass needs to be in kilograms. V sub f is the final velocity, and that needs to be in meters per second. V sub I is the initial velocity, and that also needs to be in meters per second. So just make sure that you are looking at the units in the word problem and converting if necessary. So that's why it's always the first step when we approach physics problems. Notice we have two equations for impulse. So you're going to need to identify and look through the information given in the problem and figure out which equation best applies. So the second equation is force times time. Force, F, needs to be in newtons, and then time needs to be in seconds. So just double check those units before using the equation. All right, so here are a few problems that we're going to look at. So I have a supplemental video on how to solve these problems, and I start by going through and checking the units. Okay. So kilograms, meters per second, and then down here, notice we have grams. So always check units first. When I approach this problem, the first step I'm going to do is change this 410 grams to kilograms. Okay. Same with the second problem. So the second problem, my first piece of information is 52.1 grams. So that's going to need to be changed into kilograms before using it in the equation. So some notes on impulse. Impulse always occurs in action-reaction pairs, very much like force. When we looked at force in Chapter 5, it was always action-reaction pairs, right? Whatever force you apply on something, it's going to apply an equal and opposite force back on you. That's one of Newton's 3 laws of motion. Okay? So an example would be if you calculate the impulse for two objects in a collision, and I'm going to show this in the video, I'm going to do the actual calculations, you will see that the forces are equal and opposite. Okay, so you're going to see that there's actually going to be a collision between two vehicles. I'm going to calculate the impulse, the change in momentum of one of the vehicles, and it's going to be positive. I'm going to get a positive answer. Then I'm going to calculate the impulse on the other vehicle, the other car in the accident, and it's going to be the same magnitude, so the same number, the same value, but with a negative sign. Because when those objects collided, their impulses, their forces, were equal against each other, but in opposite directions. So that is shown with a positive and negative sign, equal and opposite. Also with impulse, an important thing to remember is that the longer impact time, so the longer contact time, is going to mean a smaller force. Okay, and some examples that we looked at was padding in gymnastics and padded dashboards, but there are a few more down here, one being styrofoam, product packaging. So the reason they have styrofoam, or now a little bit more environmentally friendly, they fill up those bags with air. They do that for a cushion, for longer contact time, so that the products in the package don't get broken. They have a longer contact time, so contact time goes up. The force those products feel go down so that they don't get broken. Catcher's mitts, boxing gloves are also good examples as well. Now let's look at collisions. So I mentioned collisions briefly on the last slide. When there is a collision, what you're seeing is a change in momentum. So there are two types that we're going to look at. We're going to look at an elastic collision and an inelastic collision. For elastic, it's when two objects bounce off of one another and go their separate ways. So they hit, bounce, go their separate ways. So the image I have here is Newton's cradle. Those balls that hit and then go back and forth, right? You see a collision and then they bounce off each other and go opposite directions. Okay, so that's an example of elastic. For inelastic, this is no bounce. So the objects are going to hit, they're going to stick together, and they're going to move off together in the same direction with the same velocity. So oftentimes this would be a car crash. You see two cars hit each other or rear-end each other, and they are now combined by their bumpers, and they're moving off together in the same direction at the same velocity briefly. So for elastic collisions, a few more examples. One would be playing pool. So when you play pool, you hit the cue ball. The cue ball hits another of the balls, and they bounce off of each other. They go in different directions. So that's elastic because they're hitting each other, but they're not sticking together. They're bouncing off, going in separate ways at separate velocities. Dribbling a basketball is also an example of an elastic collision. The ball hits the ground and bounces back up. They don't stick together. So the ball colliding with the ground and bouncing is an elastic collision. For inelastic collisions, a few examples would be one, a football player tackling another football player. Okay, so in the picture I have shown below, that would be classified as an inelastic collision because the two players are colliding, but they're sticking together and going down together. They are now one object going to the ground. Big fish eating a little fish. Now I know it's not a classic collision, but all of the boxes are checked. It is an inelastic collision because you have a fish, big fish, swimming around, one mass at a certain velocity, then you have a little fish by itself swimming around at a different velocity. When big fish eats little fish, they now become one object going in the same direction at the same velocity. So it is an inelastic collision. It meets all the criteria. Two things colliding, sticking together, and then moving off together at the same velocity. The law of conservation of momentum states that the initial momentum is going to equal the final momentum. What that means is in collisions, momentum is conserved. This applies to all collisions, whether it is inelastic or elastic. So since momentum is conserved, we are actually going to look at an equation that sets the momentum before the collision equal to the momentum after the collision. So let's look at what that looks like. Some facts about momentum. So it's a vector quantity. So if you remember way back in chapter 4 when we talked about vector versus scalar quantities had a magnitude but no direction. Vector quantities have magnitude and direction. So since momentum has velocity in it, velocity is a vector, so momentum also has to be a vector quantity. The units for momentum: kilograms times meters per second. Notice that's also the units for impulse, because impulse is just the change in momentum. So it's going to have the same units as it when you calculate momentum. If two objects are involved, momentum can actually be added. Okay, and we're going to use this equation on the next slide in a collision problem. Also, momentum's conserved, so that's why we're able to set the initial momentum equal to the final momentum. And lastly, a net force is required to change an object's momentum. So when we looked at impulse, change in momentum, we needed a force applied over a certain amount of time to change an object's momentum, right? If an object's moving, how do you stop it? With a force. So that's all that last bullet point is implying. So elastic collisions. So there's a lot of information on this slide, and what all this information is doing is it's using the conservation of momentum and the fact that if two objects are involved, momentum can be additive to come up with this equation down here. Okay? So this equation is given to you on your equation sheet, and it is the equation used for elastic collisions. So this is just showing the steps on how we come up with this final equation for elastic collisions. Notice that there's an M1 and an M2 because collisions always occur between two different objects, and those two different objects will have two different masses. Notice there's also a V1 and a V2 because those two objects are going to also have their own velocities. We are not going to be calculating elastic collisions. I just wanted you to know the properties with elastic collisions. We are, however, going to be calculating problems for inelastic collisions. So for inelastic collisions, notice the equation's a little bit different. So before the collision, we have an object 1 with a certain mass and a certain velocity, and we have an object 2 with a certain mass and a certain velocity. So two separate objects going their own way, going their own velocities. But notice what happens after the collision. After the collision, there's only one velocity, and it's called V final. The reason there's only one velocity in an inelastic collision is because those objects that collided are stuck together, because that's the definition of an inelastic collision, two objects colliding and sticking. So when they're stuck together, they have the same velocity because they are now one object. This is also why the masses are being added together. Because those two objects, so think of football players, when they collided, they are now one object. Their masses can be added together. They are one object going at one velocity. When we use this equation, we're going to be calculating this final velocity here. So let's look at a quick example of an inelastic collision. So we have a grandma and her grandson. They're roller skating. So grandma has her own mass of 80 kilograms and her own velocity at 6 meters per second. So this would be my, before the collision, my M1 and my V1. Now the child has his own mass, so I'm going to call that M2, of 40 kilograms, and his own velocity, this would be our V2, of 0, which means he's not moving, he's standing still. So grandma comes along and scoops up her grandson, causing an inelastic collision, because now look at them. They are now one object, moving at one velocity. So after the collision, their masses are the same. Okay, grandma M1 is still 80 kilograms, and grandson M2 is still 40 kilograms. So we add those masses together after the collision, and their velocities now are the same because they are now the same object going in one direction. So excuse my sloppy writing here, but this is our VF that we're trying to solve for. So pretend those are F's. All right. So when we approach these problems, we're going to convert if necessary. That's going to be our first step. We're going to write down and label all our knowns and unknowns, and then we're going to plug them into the inelastic collision equation and solve. Okay, so I have a video showing how to solve these problems. So here are the problems that we are going to look at in the video. Okay, notice we have two cars colliding and sticking together, so it is an inelastic collision, and we're calculating the final velocity in the end, that V sub F. Look at another example, in this case, two speedboats colliding, and this is also going to be an inelastic collision. So we're once again calculating that final velocity of those two speedboats colliding and sticking together.